happy to give this talk. It's the first time I give a seminar on this, so even the test audience. I started this just after I finished my PhD, and it got like delayed and stuck and whatever. So I never finished until recently. Yeah, and we're talking about penguins, and apparently at some point in these past 10 years work, it must have come out that I work on penguins, so I got actually an invitation. So they learned that I published on penguins, and they invited me to write a paper on the environmental influences, dietary behavior, and conservation strategies.
The Z paper is the new title.
Yeah, it's totally amazing field of study. Okay.
There you go.
I think this paper will take me more than 10 years to finish. Okay. So what traditionally we use penguins for, so penguins is a fancy word of a transition that is forbidden in the standard model. It's a flavor changing neutral current transition. So for example, you can have the change of a B quark to an S quark via a loop diagram. So in the standard model, this is always induced by a loop. And this makes it very sensitive to new physics contributions, which is something that we are always looking for, and we somehow didn't really find something convincing yet, but we keep looking. And there, like, if we look with flavor precision observables, there are a bunch of interesting observables. For example, rare decays, for example, ES2U decay, which was measured recently by LHCb and CMS. So these rare decays have branch interactions of 10 to the minus 9, or for the rare KM decays, they have branch interactions of the order 10 to the minus 10, 10 to the minus 11, and there are dedicated experiments to look for them. And so these are very small, and they're sensitive to new physics contributions. Also, the famous B2K star L plus and minus angular distribution, so we see kind of, depending how you the fit and how you believe the standard model predictions, we see kind of around 4 to 5 sigma tensions, or the RK ratio where we now probe lepton level universality, and it's also away from the standard model prediction. And all these decays, they receive contributions from loop diagrams of this form, and this is what I call the Z penguin. Okay. So how do we use these decays to look for new physics? So there are kind of two strategies. Kind of the traditional approach is you take a model, let's say the MSSM, 2x double model, Sled box, whatever, like any model you like, you calculate the Z penguin, and then you compare to data, and you get constraints on your model, or hopefully in the future discovery. It's kind of the traditional flavor physics method. Then, since this was not so successful, and you didn't want to go like more and more models, now what became fashionable recently is to say, okay, we didn't see any new physics yet at the LHC, so let's construct just a general effective theory, standard model effective theory, where the new physics degrees are heavier than the electric scale. It's called the standard model effective theory. And then you just start constraining all these operators. Okay. So this has also kind of a problem, because so in the end you don't want only to look for new physics in flavor physics, but also at LHC. And then it's not so easy to connect these precision methods to LHC searches, because the effective theory is not valid at the LHC. Okay, unless new physics is extremely heavy. Okay, so now kind of our question was, how can we connect the virtues of effective theory that is relatively general, so you don't have to specify a model, with the virtues of UV complete models. So if you have a real renormalizable model, you can immediately calculate consistently LHC observables. Okay, and the observation is, so what actually makes a real model useful at LHC is that it has a, let's say, a sound UV behavior. So there's no unbounded growth of scattering amplitudes. This is what we call perturbative humidity. Okay, and this UV behavior, which controls kind of the high energy behavior at the LHC, also controls the high energy behavior if you calculate the loop. So it controls the renormalization properties of the loop amplitude, and it's actually exactly the same condition. And so we use this to calculate, like in UV complete models, but without specifying a model, just using these general relations that fix the UV behavior. Okay, and this way we want to combine these two pictures. Okay, so this is the outline. I will talk first a little bit about the sea penguin. So a quick reminder about what is flavor physics, how does it work in the standard model, how do we extend from there. And then I want to show you in detail how we calculate this sea penguin amplitude. And I will not go into the calculation of the loop diagrams, but just give you the structure of what goes into, what ingredients go into this calculation, and how can we generalize this to like arbitrary models. Say. And then there should be some pheno in this talk. So I want to give an application of how we can use this to look for new physics. And I want to give kind of an interesting example. I want to use flavor observers to constrain actually flavor conserving couplings. So it's like something we don't immediately think about. And I will use this to compare like the EFT method to our method of having a full calculation. Okay, let's go on the EFT section. Okay, so let's start with the set penguin. So in the standard model, all flavor dynamics comes from the CKM matrix, which controls the couplings of the charged W bosons to the quarks in the standard model. And so we are in particular interested in transitions that are forbidden at 3 levels. So we have to go to 1 loop level, and these are, for example, flavor changing couplings of the C boson to quarks. So they are induced by loop diagrams, for example, this set penguin diagram. And the whole dynamics in the standard model comes from an interplay between the CKM matrix elements and this loop function. So this function is just a function of the quark masses and the W mass, and these CKM parameters are given by the CKM matrix. So the CKM matrix has a certain hierarchical structure, so all these off-diagonal transitions or intergenerational transitions are suppressed. So we can parameterize this in terms of this Wolfenstein parameter. And also these quarks have different masses. You know, the top quark is really heavy, the other quarks are very light. So depending on the external states, you get like a different pattern of decays for the different flavors. Okay, so that's generally the picture. There's one important property of the CKM matrix. Just by definition, the CKM matrix is unitary, which means if you take 2 different rows or 2 different columns and multiply them, you get 0. And this is exactly what enters in these set penguins. So you sum over the internal quarks, which gives you effectively a multiplication of 2 rows. And because it's 0, it means that anything that does not depend on the masses of the internal quarks adds up to 0. That's why these functions are purely functions of these quark mass ratios. And in particular, this leads also to a cancellation of the divergences of these diagrams, because the divergences are mass independent. Okay? And this effect is called the Jim mechanism. So this partial cancellation of amplitudes because of unitarity is called the Jim mechanism. So in particular, if all the quarks at the same mass, or all the quarks were 0, then the whole thing will vanish. Okay. So now I mentioned perturbative unitarity. What is that? So a classical example of perturbative unitarity is if you look at the W scattering, just with the exchange of gauge bosons in the standard model, so it's Z or gamma. And then if you compute these amplitudes, you see the contributions of these amplitudes give a contribution which is proportional to S or T, so the center of mass energy or T, so the Mandelstam variables. Okay? So this is not good at high energies, but it turns out why, for example, is the C massive? You need a Higgs mechanism. So if you add like an explicit Higgs mechanism, for example, the standard model Higgs, and add the contributions of the Higgs, you see that this leads to a bounded high energy growth. So there's no term, so these terms that are proportional to S, they just cancel. Okay? This is well known, and this relies on an intricate cancellation between different diagrams. In particular, it relies on relations between couplings of the W to the C, to the gamma, and to the Higgs. Okay? And these relations are related to the underlying gauge symmetry of the model. So this is a spontaneously broken gauge symmetry, and these like the equivalent of the Ward identities in spontaneously broken theories are called Slavnov-Taylor identities, and they give relations between these couplings that ensure that this high energy growth, this large high energy growth cancels. Okay. So, how does the cancellation, the other high energy cancellation work for the Z penguin? So let's just look how we calculate the Z penguin in the standard model. So we write down all diagrams, all Feynman diagrams. So they have Feynman diagrams with W exchanges. Depending on the gauge, there might also be Feynman diagrams with the pseudo-Goldstones, so they're eaten by the W's and so on, all kind of mixed diagrams. Okay? And then, of course, you complete the loops and you need to give inputs for the coupling. So they're the couplings of the W's to the quarks, of the C to the W's, of the Z to the left-handed and right-handed quarks, and also all the couplings to the pseudo-Goldstone bosons. So if you just do an naive calculation, you need all these couplings. What will turn out, what I will show you, is that in effect, you need only these blue couplings. You need to specify only these couplings. All the other couplings are fixed by gauge symmetry. In particular, the red ones are unphysical. You can get rid of them, and these other ones are also fixed from the high energy case. Okay. So in the standard model, if you do the calculation, there are kind of two steps to make this calculation finite. The first step is what I mentioned already. You use the Gym mechanism. So you use the unitarity of the CKM matrix. You can eliminate one of these combinations of CKM parameters to eliminate them in terms of the other two. Okay, this leads to a cancellation of many of the diagrams. And then what you will find is actually there's still one leftover divergence if you just do the calculation, and this divergence is proportional to exactly this combination mw squared minus cosine of squared of the weak mixing angle times the cosine mass. Now you know, of course, that the cosine of the weak mixing angle is just given by the ratio of the w to the cosine mass. So if you use this relation, this contribution will also vanish. Okay, and then you get final result, which is the well-known standard model result for this penguin, which is given just in terms of this ratio of the top log mass over the W mass. Okay. So, in fact, these relations are of course not coincidental, but they follow from some rules between couplings that are related to the Slavnov-Taylor identities that control the high energy behavior of the theory. Okay, so what are these Slavnov-Taylor identities? Just on a technical level, okay, in order to quantize a theory, you need to introduce a gauge fixing term, okay? Also in the spontaneously broken gauge theories, there's a gauge fixing term, and this completely breaks the gauge invariance, but it turns out that there's an underlying symmetry, which is the Drst symmetry, which reflects the underlying gauge symmetry of the unbroken theory. And you know the Ward identities from QED, they correspond to the U1 gauge invariance, so now these Slavnov-Taylor identities, they correspond to this Drst invariance, which is related to the underlying gauge symmetry of the non-abelian gauge theories. So, practice, what this means is, so typically you add a gauge fixing term for the massive vector fields, which is given in terms of the derivatives of the vector fields, and then another term that removes the mixing of the vector fields and the pseudo-Goldstones. It's kind of an arbitrariness here, but you can do it in this way. Then you can use the fact that all physical on-chip fields are Drst invariant. Okay, if you take matrix elements of Green's functions. So then you can obtain some rules between couplings by doing the following trick. So you take Green's functions between any number of physical fields, thermal fields or physical vector fields, times an anti-ghost field, and the Drst variation of the anti-ghost field is exactly this gauge fixing term. That just comes out from how we quantize these theories. Okay, so and this thing is zero. Okay, that's the Slavnov-Taylor identity, and this gives you relations, for example, that relate vector boson couplings, Goldstone couplings, and couplings of physical fields. Okay, so for instance, just as an example, if you choose as your physical fields the two fermion fields, an anti-fermion field and a fermion field, you see that this Lovelock-Taylor identity leads to a relation between couplings of these pseudo-Goldstones to the fermions in terms of the couplings of the fermions to the physical vector fields. Okay, so there's just a relation like this. So you can use this relation to eliminate all the unphysical Goldstone fermion couplings in terms of physical vector fermion couplings. Okay. Then you choose different, by choosing like different fields for the physical fields, vector fields, and combinations of vector and Higgs fields, actually allows you to eliminate all the couplings of the unphysical Goldstone bosons. In some sense, it's kind of trivial because you know that you can gauge them away, but you can do this like in gauges where it's easy to calculate new amplitudes, so even not in unitary gauge. So just show you this formula. The details are not important, but you see any. So this phi is always the Goldstone, so you can replace any of these couplings that involve a Goldstone in terms of physical couplings. Okay, so that's the first step. Okay, so now instead of discussing like the most general Z-penguin amplitude, let's just start with a simple example. Let's say we take the standard model, we just add charged heavy vector fields. So we just we keep the standard model fermion content as it is. We don't touch the scalars like we just add heavy fermions, heavy vector fields. Okay, so we just write down a Lagrange where we have some general couplings of vectors to, so P's are projected to right or left-handed fermion currents, and then we have some self-interaction of the vector fields. Okay, and then we set out to calculate the Z-penguin. Like as we would do in the standard model, we write down all the diagrams that appear. Now we have lots of additional heavy vector bosons, and again we find that the general result is divergent. Okay, even after we replace all the Goldstone couplings. Okay, so what do? So we learn from our experience in the standard model. So first of all, we find a generalization of the Jim mechanism of the CKM unitarity. Okay, again, by choosing an appropriate set of physical fields, we get some rule of couplings that relates the couplings of fermion to vector fields and the vector self-couplings to another set of vector fermion couplings. Okay, so that's just the general rule that comes out. If you, just to get an insight what this rule means, let's look at this rule just in the context of the standard model. So let's say the F would be the B and the F2 would be the S, so this is a B to S transition. And the heavy vectors would just be the standard model W bosons. Then, so since this is a B to S transition, so the left-hand side, so this has to be a neutral boson. The only neutral bosons in the standard model are the C and the gamma, and they don't have off-diagonal couplings, so the left-hand side vanishes. Okay, and on the right-hand side, only the second term is left over, and what you see is you get just this relation that if you sum over fermion fields, the product of these W plus W minus couplings is 0, which is precisely the statement that the CKM matrix is 0, because in the standard model these couplings of an up and a down type for W's is just proportional to the CKM matrix element. Okay, so this is a generalization of the CKM unitarity. Like now you learn actually that in any theory where the couplings of the neutral gauge bosons are universal and diagonal, then always the couplings of the charge bosons are related to a unitary matrix. Okay, so you always get a Jim mechanism. Okay. Conversely, if you have FC and C level changing neutral current couplings at tree level to the C bosons, then the CKM matrix will not be unitary. Okay. That's what we learned from this rule. So if they are, then we get something like a generalized Jim mechanism. Okay, so we expect some cancellation of amplitudes. Okay. So in the standard model, that was okay. Another, I wanted to show another. How can we view this relation in terms of diagrams? So let's say we set out to calculate these diagrams, and we will find diagrams like this, where we have a gauge boson, triple gauge boson coupling, and diagrams like this, where the gauge bosons coupled to the fermion fields. Okay, so now this sum rule that we found kind of relates, if you imagine you kind of cut the diagram open here, that you see this kind of sub diagram, tree-level diagram is just a sum of these internal vectors. That would be this sum. And here, if you cut this diagram in an analogous way, this would be a sum over the internal fermion. And these couplings here, they're related. So the sum relates like the values of these diagrams, or the infinities of these diagrams to each other, such that they cancel. In the standard model, we need the other relation, that the C and the W mass are related. And this is also follows from another coupling sum rule. Okay, this coupling sum rule looks quite horrible in the general case, and this is only the general case that you add only heavy vectors, okay, no scalars yet. Okay, but again, if you just plug in standard model values for all these couplings, most of the stuff vanishes. Okay, if you choose suitable external states. And you see that this thing just boils down to this relation that MW squared equals the cosine of the mixing angle squared times MC squared. Okay? So this relation is just a generalization of this standard model relation. Okay? Again, you can use these relations between couplings in your general diagrams, and it turns out you get rid of all the remaining divergences. Okay. So in this way, you can get the full result, but for the Z penguin, if we add arbitrary heavy vectors to the standard model. Okay, so we use this generalized Gin mechanism, and then to further sum rules, and we can use this technically to just eliminate all C-boson couplings and all couplings to light quarks. We can completely eliminate them. Okay, and in this way, automatically all infinities cancel, and we get a final result. And this is the result. So the Z penguin is somehow proportional to only the couplings of the C to the heavy vectors and of the charged vectors to the standard model fermions times a loop function that is completely general. Okay, like it's completely just one loop function, and in particular it's finite. Okay, it's a finite loop function. And what is kind of interesting is it depends really only on the reduced set of physical couplings. So if you want, let's say, if you want to fit your general model to data, it's very nice that you have like a minimal set of couplings so you don't overfit, because most of the other couplings are actually fixed by the sum rules. Okay, so that's kind of a minimal expression for the set. Just I can show you this loop function exists. It looks like this. It's given in terms of this 3-point function, which is just a symmetric combination of the masses and logs. Okay, it looks kind of horrible, but the nice thing is it's there and you never need to compute it again. Okay, just plug in the values of your coupling constants, you get the set penguin. Okay, so let's take a deep breath and.
So the net result claim that the Z penguin will always one page back further than next slide. Does this claim the Z penguin will always vanish for something that is vector bosons that the Z doesn't couple directly to?
Yeah. Yes. Let me think about this. Yeah, probably. Yes. That would be the claim. It probably would be inconsistent to have this C coupling only to the fermions and not to the gauge bosons. It would probably violate one of these sum rule relations. So it would probably mean that your model is not irrenormalizable.
I guess that's because I only have the standard model fermion.
Yes. 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 Mm-hmm.
Okay.
Yeah, exactly. Yes. This is the special case that we have only charged additional vectors. Right. So what happens if you just allow for everything? So we allow for let's say new scalars that couple to left or right-handed fermion currents, new vectors that couple to left or right-handed fermion currents. So again, we have our self-couplings of the vectors and then couplings of the scalars to vectors, and in this way. So we can just again generalize from what we did before. We just get all the Slavnov Taylor identities to find a complete set of submodel relations. Okay, and then we can use these relations. Okay, then we calculate all final diagrams that we can run down, and we use these submodel relations to replace the couplings. Okay, and then as before, you can see that we find a result that is manifestly finite, so it depends on finite loop functions. And again, it will depend on the reduced set of physical couplings, because we can use our relations, first of all, to get rid of all unphysical couplings, and then we have more relations that allow us to eliminate physical couplings, thereby making it finite and thereby making it dependent on a reduced set of couplings. Okay. So, without showing you all the full generality of the coupling submodules, here's the result. So that's the most general result if the having particles are charged. Okay, so if you add all the vectors, they have to be charged because the charge is fixed by the external state and by the Perturbative content. In the general case, you can also have neutral having particles. And this is just the result if they're all charged. So to obtain this result, there's always an arbitrariness, like which couplings do you eliminate and which do you keep. This kind of, I don't know, it's a choice. And here we eliminated all the couplings to light standard model fermions, so there are no couplings to up and sharp quarks. And we eliminated all diagonal set couplings. Okay, so we can do this in general. Okay, and then all these couplings are left over, and these functions, they're just finite functions. It's nice they're finite because then they're easy to evaluate its molarity if you want. Okay. I don't show them, but yeah, that's just an explicit expression for them.
Now, in general model in physics, I should have a 3-level Z coupling to BS.
Okay, that's a very good point. Of course.
And then I should get a divergent answer for this calculation you're telling me is fine.
Yes, exactly. So here, one thing we assume is that there's no 3-level coupling of the C to B to S, because then we would never calculate this loop. Okay. So this correction would then be just a small one-loop correction to a 3-level coupling. So,
but your 3-level coupling can be small.
Okay. In this case, okay, you're also right. Okay. In this case, this expression would change a little bit because you need to add a counter term for this coupling. So here we assume that this result is finite. I mean, we assume that it's not there at 3-level, essentially. Okay.
Which means, what's the equivalent physical assumption? That's telling me that I have no mixing of different fermions with different SU2 representations, something like that. Into the quarks of interest.
Yes. Okay, it's kind of one more. Yeah. It's one assumption. I mean, obviously, this method would also work if you have read the same thing. Just additional concepts. Okay, so now we have our general result. Now let's talk first about a slightly different topic. So let's do some pheno and let's see how can we constrain anomalous couplings of the C boson to the standard model top quarks. Okay. So the first thing that you would think of course, is we go to the LHC, we produce a top quark pair and a C boson, and we look for this, and then we get obviously a constraint on this on anomalous contributions to these couplings. And then it turns out, if you do this, the constraints are actually extremely weak. Okay, so this has been, so QCD corrections to this process have been calculated, so the NLO expressions are known, and it turns out even with 3 inverse atomar of data, so high Lumi LHC, you still allow for 20 to 30% deviation from the standard model couplings just based on LHC data. Okay, so then you can wonder, okay, is there any other way to constrain this coupling? Okay, and then what you can do is, okay, So we have this anomalous TTC coupling. And the idea is, okay, let's just take a standard model gauge boson and add it to this vertex. And what we generate is, among others, we generate a B2S transition. Okay, so in other words, we generate a C-penguin. And this is strongly constrained from flavor data, just by comparing to, let's say, the QSB transition, which is measured by CMS and LFCB. Okay, so that's kind of the general idea. And then, so how do we explore this idea? And like the easiest thing is to go to an effective theory approach and see what kind of constraints we get. Okay, so let's first start with an effective theory. So now we want to write down all operators in the unbroken standard model effective theory that upon electric symmetry breaking generate an anomalous TT set coupling. And there are only a few. Okay, so let's say you have some physics at high scale, much higher than the electric symmetry breaking scale. So you integrate out your degrees of freedom, you generate a bunch of operators, and the only ones that modify the top C couplings are these ones, the ones that have this Higgs vector current. So this D is a covariant derivative which has essentially a Z field inside. Okay, and then this third generation core currents, left-handed and right-handed core currents. And note that in this doublet, there's not only the top quark, we have also the down quark, and so we have a CN mixing atom here. Okay, so only these operators induce a tree-level TTC coupling, or modifications of the tree-level TTC couplings.
So that's why we're not talking about the dipole operators.
Yes. So we're just interested in these like chirality conserving TTC couplings. Okay, so now if we break electric symmetry, these operators translate into changes of the couplings of the C to the right-handed top quark, of the C to the left-handed top quark. Then because of this of the doublet structure of the left-handed quarks, we also will modify the couplings of the C to the down quarks. Okay, and they can even be off diagonal. And we will also modify the couplings of the W's to down and top quarks. Okay, so they're related by the H invariance. So we cannot just only modify the TC couplings. This will break H invariance. Okay, and these modified couplings are related to the coefficients of these three operators in this way. So that just right-handed just comes obviously only from this operator that involves the right-handed top, and the other ones are combinations of these triplet and singlet operators. Okay. So now, in order to proceed, in order to do our loop thing, okay, we make exactly this assumption that you mentioned. You have to somehow assume that at the high scale there are no FC and C transitions in the downward sector, because otherwise we would just be testing this combination. So let's just make the assumption that this combination, so this is the combination that has the downward transition, is 0 at the high scale. Okay? So is this a crazy assumption or not? Okay, I don't know, but there are kind of models that are not too crazy and that satisfy exactly these assumptions. And one model that you can get this scenario is if you extend the standard model with vector-like uptime quarks, or vector-like top quarks, and some representation of SE2. Okay, so and then you just adjust the charges in the right way, and you see that there will be no FC and C transitions in the downside. Okay, so but let's forget about the vector-like quarks for the moment. It's just like in general the assumption that this combination of coupling vanishes. But as we will see, these transitions will be reintroduced by RG running. So now we go from our high scale to the electric scale. So we assume at the high scale we modify these TTC couplings, and then we calculate the exchange of a W boson. If you are only interested in the log enhanced piece of this, we can just use RG method, randomization group methods to calculate the log. In fact, this is all known, so we don't need really to do the calculation. So the EFT will kind of easily give us the logarithmic term. Okay, so we evolve this down. So at the weak scale, we get this V2S transition, which now depends on these modified TTC couplings, and we can compare to the data. Okay, so by RG, running, we modify the rare decays of the mesons. In fact, because this just comes from the standard model CKM factors, there could be also a B2B transition, for example. So it's not only that we modify B2S transitions, we also modify flavor diagonal transitions. Okay, and in fact, there are several contributions. So this RG mixing in full generality will introduce modifications of BBC coupling. So this is very well measured at lab. So this is a strong constraint. It will modify decay rates for K mesons. Okay, and it will also induce a contribution to electric precision observables, in this case the T parameter. Okay, so we can take all these constraints and do a fit, okay, and see what are our constraints on the TTC coupling. So do this, just show you the analytic results. So these are our original coefficients of the modified C couplings, and they introduce along this BBC couplings, modifications of the T parameter, and modifications of the loop functions that enter the rare meson decays. And we always pick the log because just by using EFT. Okay. And that's how it looks like. That's how it looked like a couple of years ago, but the data didn't change that much. So the current situation is like this: that you have a relatively weak constraint from modified Z to BB coupling. So this is lab. Okay. Then VS to mu, which is measured by CMS and LHCb, gives this red band, and the green band is the T parameter. Okay, so the green band is kind of electric precision, and what's kind of interesting is that already now the constraints from the rare meson decays are like similarly constraining than the ones from electric precision. And then if you go to like future projections, so say a 5% measurement of BSU and measurements of the rare KM decays by NA62, which should be done about this next year, you see that you get actually like a very strong constraint. So you can constrain these anomalous couplings to percent level, okay, which is nice and complementary to LHC searches, which give you a much looser constraint. Okay, of course, it's an indirect constraints, okay, but they're very powerful. Now finally, I just want to come, so now we can go back and we can look at the real model, because now we have, so now we did the analysis in DFT, but we can now do the same thing in a full model. And I didn't do the numerics, but we can now test some assumptions that we did, for example. So we can, so in the EFT we just compute the log enhanced piece, but of course the question is this a good approximation? What about the finite pieces? So the finite pieces you can never calculate in EFT, because in EFT they're always independent. You can only calculate the log. So in order to say something about the full amplitude, we have to specify a model. But kind of this general approach, you can just, it's easy to specify a model because we have the result already. Okay. And so I want to go back to this model of adding just a vector-like top work, because this fits nicely the assumptions that we made in the EFT analysis. So let's say we augment the standard model by a LC2 singlet vector-like top, just as an example. So we just add a top and a vector-like representation, and we add an additional U-cover interaction that mixes this. The top is unfortunately called U, so this would be the vector-like top. So there's an additional U-cover coupling that couples it to the standard model and it works. Okay, and then we do the same thing as in the standard model to get our finally. So we go to the mass eigen basis. So we diagonalize the U-covers, which of course is not completely possible. So we have to kind of, the misalignment, we shift it into the couplings to the W. So we introduce some kind of CKM matrix. Okay, because so it turns out that this. If you just add a vector-like top work, then you induce FCNC couplings to uptype standard works. So just from our general considerations, you know already the resulting CKM matrix, quotation marks, will not be unitary. In fact, now it's a 4x3 matrix because you have kind of 4 uptime quarks, 3 downtime quarks, so it cannot be unitary. But again, it's clear from general grounds. Okay? But anyway, you can work out all the Feynman roots by doing the rotations. You see how the couplings are modified. And now, to calculate the set penguin, in addition to the unmodified standard model couplings, we need to specify only very few additional couplings, namely the FC and C couplings in the up sector, which is given by a product of this particular product of the CKM matrix, which with the dagger might be probably inside the flat. And then the modified couplings of the W to up and down course, and that's the best. Okay, no calculation to be done because we did the calculation already. We just plug in the couplings. Okay, and then we get the expression for the set penguin functions, which looks relatively complicated, but it just comes out from plugging in the couplings into the general result. Okay, so it's given just again similarly to the standard model case, is given in terms of this ratio of top work mass to W mass and this new vector like top mass with the W mass, which is called X and Y, and these are little functions which are again defined. Okay, so that's the full result. And now, okay, I didn't do any numerics for this, but we can compare this to the EFT approach. So in the EFT, if you want to reduce this to an EFT approach, we just take this mu to be the scale lambda, so we have to make this mu very heavy. Okay, so it kind of like the set penguin should go like 1 over mu squared plus high order corrections. What is kind of interesting, if you look at these loop functions, they don't behave like this, so they have lots of constant terms which don't decouple like 1 over mu squared. So this is a bit tricky to see. And what you need to do is you also need to take the same limit for the CKM matrix. Okay, because also the mixing angles in the CKM matrix that depend on these rotations in the recover sector, so they implicitly depend also on angle. Okay, so it turns out, a kind of a long calculation, that in the large mass limit, the CKM matrix looks something like this. So there's just the standard model CKM matrix, and then there's a correction term, which for large M looks something like this. It was like x left or mu times the recover couplings in the new sector times the standard model of the CKM matrix. And then this VB dagger, which enters the FC and CC couplings, looks like this. So you see in this large mass limit, you actually don't induce any FC and Cs in the up sector. And using these explicit expressions, you see that like all terms go at least like 1 over m squared. Okay? And you can actually go back here, just pick all the log pieces, insert the couplings, and compare to the EFT result. And we use this as a check of our general result. They perfectly agree. So the log terms in the EFT and the log terms that we compute in this special model, the exact correspondence. Okay. And then you can do things. You can check, so you can compare the log term to the finite pieces, and then you see that for all these rarity cases that we looked at, the log terms are always larger by at least a factor of 4 or factor of 7. So this is kind of, in this case, it was a good approximation to use the EFT. If you want to play more, you can look at the dimension 8 operators, and you see that the dimension 8 operators are completely negligible. So in this setup, using an EFT is actually a good approximation. Okay. But this kind of is more general. So if you have the general result and we don't go to the large mass limit, you see there are actually more observables. For example, there are flavor changing neutral current mixed couplings. So you could, for example, if you want, you can look or search for rare top decays, like top goes to X and then up, or top goes to X and sharp. So there you open up more possibilities to test this model. That's something we wouldn't see in the EFT. Okay.
Those things exist in the EFT, they're just different operators.
Yes,
If you matched this model into the EFT, you would also see that.
Yeah, that's actually, yeah, that's true, because we looked only at the operators that we specifically changed their C complex. Yeah. We should see that. Okay. So that brings me already to my conclusion and outlook. So what I showed you is that, so we have developed a, I think, nice and general method to calculate lead-induced observables. And for the moment, I just, we have done this for the sea penguin, but the method generalizes to all kinds of other observables that are lead-induced. And the nice thing about this is that in principle you can probe collider and precision physics in a consistent way. So if you use only EFT, then it's sometimes doubtful if you can apply this in a C context always. So I showed this in for the context of the sea penguin, but you can easily generalize this approach. So you could, for example, so the nice thing is there are not so many observables that are forbidden at tree level in the standard models. You can just do this in addition to the sea penguin for the photon penguins or BTS transitions, or also for the flavor conserving photon penguin, otherwise known as magnetic dipole moments, so G-2 for the muon, let's say, or electric dipole moments. So they can all be calculated in this general way. Or you can look at the loop-induced Higgs decay 6 gamma and so on, electric precision tests. And then if you allow for, let's say, not standard model external states, but let's say dark matter, you can test, let's say, dark matter with dipole interactions. So these are all kind of straightforward generalizations of this result. Something we work on, and I think this is maybe not something that you want to use analytically and like type all these formulas and put in your model, but this is something that you can easily program into a computer code. Okay, you just program the general form of the observables, then you just specify your couplings. You can maybe even automatically test that all the sum rules are satisfied, so you know you have a really consistent model, and then you can compare this, let's say, automatically to data. Okay, that's all I wanted to say.
Thank you very much. Are there any questions? So what would the automatic fitting tool be doing, given that, say, Sarah and other things do a lot of these things already? It's just much more efficient than